In this problem, we're asked to determine the principal stresses at point H here on the shaft. The pulley is rigidly attached to the shaft, so they rotate together. And the diameter of the shaft is 1 inch. Now I went ahead and drew a cut section here right before point H of the shaft. So you can see here. Now if we think about the effect of this load at this cross section that I've drawn, we can equate the effect to 3 different loads. So there is a effect of the load, translating P. There is a bending moment across this axis, call that M. And there is a torque across this axis, call that T. Now if I want to take a look at what's happening on the stress element, H, when you think about it, in the planar region of plane H, the effect of P is having no effect, just in the planar region, if we're considering the planar stress element only. The bending moment is causing tension on the stress element, or bending normal stress. And the torque is causing shearing. So there will be a shear stress acting on this element. Call that tau T. And in this planar element, there really are no other stresses acting in this region. So, in order to determine the principal stresses, we need to figure out what the current state of stress is. In other words, we need to figure out the values for these, and then we can apply equations to find the principal stresses. So let's start with the bending normal stress. So sigma M is equal to MC by I, right? Okay. What is M? M equals FD. Maybe I'll call it PD since I've written PD. So that's 400 pounds. And that bending moment is acting at a perpendicular distance of 6 inches. So this would be 6 inches. My pound looks like a 16, doesn't it? Let me correct that. Pound. That's a little better. Okay. So that's equal to 2,400 inch-pounds. Okay. What about the torque? We'll go ahead and calculate that since we're doing this. So the torque is 400 pounds acting at a distance of the radius of the pulley, which is going to be 2 inches. PD. Well, I'll say PR equals 400 pounds times 2 inches equals 800 inch-pounds. All right, back to the stress. We know the moment, we know the radius of the shaft is a 1/2 inch. So this is going to be, well, we know M, we know C. Let's figure out I. So I, for a circle, is pi divided by 4 times r to the 4th. Let's call r C. Let's call it c to the 4th. Okay, so if we plug that in for here, we get 4m divided by pi c cubed. So that's equal to 4 times 2,400 inch-pounds divided by pi times a 1/2 inch radius of the shaft cubed. Plug that into my calculator. We get 24,446 PSI. Now for the shear stress calculation, this is going to be equal to the torque times the radius. Actually, let me call that radius, not C, because here in the shear stress calculation, due to the torque, I'm talking about the radius of the pulley. So here the radius of the pulley is 2 inches. In the stress case, the radius of the shaft was the C, which was just 1/2 inch. This would be the radius of the shaft, 1/2 inch. Okay, so shear stress is equal to TR by J, which is equal to TR divided by pi by 32 d to the 4th power. Right? So if I rewrite the radius as 1/2 of the diameter, I'm going to get 16t by pi d cubed. All right. So this is 16 times 800 inch-pounds. That's our torque value. Divided by pi times 1 inch cubed. All right. 16 times 800 divided by pi divided by 1 cubed. 4,074 PSI. All right, so now we know our principal stresses, or not our principal stresses, our current state of stress. Excuse me. That is incorrect. So, what's the formula to calculate the principal stresses? Let's scroll down a little bit. So to calculate principal stresses, our principal normal stresses is equal to sigma x plus sigma y divided by 2 plus minus the square root of sigma x minus sigma y divided by 2 squared plus our planar shear stress squared. All right. If you're thinking in terms of the Moore's circle, this is going to be equal to the center plus or minus the radius of Moore's circle. But here we're not really drawing Moore's circle. But important to note in Moore's circle is that if you're considering the planar region only, as we are in this case, tau max is equal to R. So that'll be key. So whenever we calculate this, whoops, sorry about that. Whenever we calculate just the square root term, that's going to be our principal shear stress. Okay. So let's go ahead and plug in numbers here. So our sigma x, if we draw a coordinate system here, consider this is our x region, this is our y region. we'll see that there is no sigma x stress, but there is sigma y stress due to bending. That sigma y stress is 24,446 psi dividing by 2. I guess I'll write a 0 out here just to be explicit. Plus minus square root of sigma x is 0 minus 24,446 psi divided by 2 squared plus our planar shear stress, 4,074 psi squared. This is going to be equal to, let's see, I can do that in my head. This is 12,223 psi plus or minus, I can't do that in my head, square root of this is going to be 12,884 psi. Okay, so sigma 1 is equal to that plus 12,223, and that is 25,107 psi. And I'm writing it in psi to keep the base units, but it would be a lot more convenient to use ksi. And this is going to be negative 661 psi. All right, so now we remember that max shear stress is 12,000, I'll go ahead and write 12.8 psi. Sigma 1 is 25.1, oh sorry, this is KSI. And sigma 2 is negative 0.661 KSI. All right, so these are our principal shear stresses. So that is how you solve this problem. So thank you for watching, and I hope you have a great day. Please comment on this video with any suggestions that you have for topics that you'd like to hear about, or any feedback on how I can do a better job bringing content to you. Please also like, share, and subscribe this video for more content like this, and have a great day.